Hello there, and welcome. Tonight, we're unraveling the secret flicker at the heart of every candle, every campfire, every rocket fire. It doesn't fit neatly into science class. It moves like a creature. It consumes but leaves no body behind. It can melt steel, hypnotize the eye, and survive without gravity. Some flames burn underwater. Others burn cold. There's even a type of fire that feeds on ice. These aren't just trivia. They're clues to how the universe behaves, how life survives, and how we've shaped the world with something we still don't fully understand. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world, like stars across the galaxy. Now, take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Fire is not a thing. That's the first truth. It looks like a substance, something you could touch if you dared, but it isn't made of particles in the way that water or stone or air are. It has no shape of its own, no boundary, no edge to hold. It is motion, it is reaction, it is energy escaping matter in a visible wave. What you see when you look into a flame isn't an object, but a process, a shimmering envelope where atoms break apart and recombine, releasing heat and light. It's not fire itself that burns. It's the air and the fuel and the frantic exchange of electrons in the space between them. And in that space, something astonishing happens. As a material heats, the atoms begin to vibrate. More heat, and the bonds start to break. Eventually, if you push it far enough, the electrons themselves peel away from their atoms and the whole structure begins to dissolve. This is what we call plasma, the fourth state of matter. Not solid, not liquid, not gas, but a sea of charged particles, free and chaotic. Fire is made of plasma, and unlike the others, it doesn't like to stay still. That flicker, that constant dance, it's not just the wind or your breath. It's the nature of plasma trying to stabilize, constantly torn between heat rising and air rushing in to feed it. Flames pulse because oxygen flows in unevenly. It doesn't burn smooth. It hiccups and curls and sways as heat draws more air toward it, and combustion ignites anew in tiny waves. The bottom of a candle flame, near the wick, glows blue. That's where the combustion is most efficient, where the oxygen and the vaporized wax are still mixing in proper ratio, burning hotter than the visible yellow above it. The yellow, golden tip, the one we usually think of as the flame, is actually glowing soot, microscopic particles of carbon heated until they radiate. They aren't burning, they're just hot enough to shine. Fire glows because electrons don't die quietly. When a molecule breaks apart in heat, the electrons around it are flung into higher energy states. They can't stay there, so they fall back down, and when they do, they release light. The color of that light depends on the energy level of the jump. That's why fireworks look the way they do. Strontium burns red, copper goes green, sodium bursts gold. It's not paint or dye. It's atoms shedding light like tiny flares. And that color doesn't just vary from substance to substance. It shifts with temperature too. A cool flame may barely glow. A hotter one turns yellow. Push it further, and it moves through blue and white. At the extremes, it can even radiate ultraviolet light we can't see, but that burns our skin and fades our ink. Fire is a spectrum, a ladder of energy that climbs through color as it climbs through heat. But even when it's cool, fire is fast. In some materials, combustion can happen almost instantly, less a burn and more an explosion. Paper burns quickly because it's full of oxygen between the fibers. A dense block of wood takes longer. It has to smolder first, converting the outer layer into charcoal before the heat can dig in deeper. In both cases, it's not the material itself that catches fire, but the gases it releases. Most solid fuels don't burn directly. They decompose, release vapors, and those vapors ignite. That's why a flame can hover, why it can rise off the wick and float upward. Fire is the visible edge of a cloud of burning gas. It wraps itself in convection, pulling air from below, lifting smoke above, always reaching, never resting. It's not just flickering, it's flowing. And yet, for all this motion, for all this heat and light, fire, is surprisingly fragile. Blow too hard, and you starve it of oxygen. Let the fuel run out, and it fades. Deprive it of heat, and it simply vanishes. There's a threshold to combustion, a line it must cross to begin, and a line it must stay above to survive. That's why wet wood won't burn. The water absorbs the heat faster than the reaction can sustain itself. The fire chokes, sputters, and dies. And still, fire is patient. It waits for conditions to change. A match won't light if the air is too thin, but it might in a few moments, when the wind calms. Fire isn't alive, but it behaves like something that wants to be. There's something almost cruel in how beautiful it looks. The elegance of a candle's flame, the quiet spiral of heat, the way light dances on nearby walls. It masks the violence of what's happening. Molecules are being torn apart, bonds are breaking, carbon is turning to gas, heat is erupting outward in all directions, and yet we stare, mesmerized. We've known fire for so long, and still, we can't stop watching it. In microgravity, it reveals even more of its secrets. Take fire into space, and it behaves like a ghost. Without gravity, there's no convection, no hot air rising, no cold air rushing in below. The flame doesn't flicker. It curls inward, a perfect sphere of combustion surrounding the wick, faint blue and silent. It looks like a bubble of heat, not a spear of light. It burns slower, too, more efficient, fewer emissions. A fire that lingers instead of leaping. Back on Earth, we see fire as fierce, but in its core, it is something very simple. A chain reaction, a transfer of energy, a balancing act between fuel, heat, and air. The fire triangle, they call it in textbooks. Remove one side, and the flame dies. But let all three remain, and it grows, stretches, consumes, and still, it remains without form. You can pour water, you can hold stone, but fire? You can only see it by what it changes. You can only touch it by being changed yourself. It leaves nothing but ash and memory. It can't be frozen or stored or built. It is a brief and beautiful ruin, remade in every second it exists, and yet it's everywhere. In the stars, in engines, in the cells of your body, fire is not a thing, but a passage, a glimpse of energy crossing through matter, flashing once before fading. That flicker you see, that's atoms saying goodbye. Not all flames look the same. Some burn high and yellow, curling in thick air with a slow flicker. Others burn low and blue, almost invisible at the edges. Some shift from orange to white in an instant, and some whisper along the surface of chemicals in strange greens or eerie purples that never seem to belong to heat at all. We think of fire as a single color, warm, bright, the color of comfort or warning, but in truth, every flame is a spectrum, and every spectrum is a story. The color of a flame is more than just its hue. It's a signature of what's happening. Inside, how hot it is, how fast molecules are breaking and reforming, what kind of atoms are shedding their light as they fall back into balance. At the cooler end, fire begins as a pale red glow, like the last warmth in dying embers. Push it hotter, and the flame turns orange, then yellow, then a fierce blue that edges toward white. Keep rising, and it begins to leave the visible spectrum entirely. It becomes ultraviolet, still burning, but no longer glowing where our eyes can follow. Temperature is the simplest cause of this shift. A red flame glows around 600 to 800 degrees Celsius. Yellow flames, like the ones from most candles, burn hotter closer to 1,000. Blue flames, clean and bright, can reach temperatures above 1,400 degrees. It's not just about energy. It's about how the energy is released. In blue flames, the combustion is more complete. There's less soot, fewer particles hanging in the air to catch and scatter light. What you see is purer, more precise. A cleaner burn makes a cooler color. But there are other factors, two subtler fingerprints woven into the flame by chemistry. Different elements emit different wavelengths of light when they burn. Copper glows green. Strontium burns crimson red. Sodium shines in an unmistakable golden yellow, a warm, sharp glare that defines the color of street lamps and science experiments alike. These aren't filters or tricks of the eye. They are the result of electrons leaping between energy levels, releasing light in narrow, specific bands that paint the flame in unique shades. When you see fireworks bloom in the sky, glowing blue or green or violet, you're watching elemental identities being written in fire. Each substance writes its own name in light. It's strange to think that something so chaotic can be so specific, that a burst of combustion can tell us exactly what it's made of. But scientists have learned to read flames this way. In forensic labs, they burn samples to see what metals or compounds might be hiding inside. In space, they analyze the light from distant stars to determine their chemical makeup, because stars, like fire, reveal their secrets through color. Sometimes, the most surprising thing about a flame is not how hot it is, but how cold it can be. Cold flames exist. They burn quietly, often invisibly, at temperatures lower than the boiling point of water. Around 200 degrees Celsius, these flames don't emit light in the usual sense. They don't roar or flicker. They don't even feel hot unless you're close, and yet they are real. In carefully controlled environments, low pressure, specific fuels they ignite and consume, slowly and steadily, without the telltale glow. They are fire without firelight, heat without flame. A contradiction that still manages to burn. Cold flames challenge our assumptions. We're used to thinking of fire as synonymous with danger, brightness, and heat. But combustion isn't always violent. It can smolder, in silence, hidden in engines or chemical reactions. It can rise from the vapor of jet fuel without ever casting a shadow. It can eat through material while remaining nearly invisible. Cold flames have been studied in space, where microgravity allows them to persist longer than on Earth. In the absence of strong convection, these delicate reactions unfold like scientific secrets, slow and haunting. Some of the most toxic fires don't glow at all. In industrial accidents and enclosed environments, smoldering fires can consume oxygen and produce carbon monoxide long before any visible sign appears. No light, no crackle, just the quiet rearrangement of matter into something deadly. Fire is not always theatrical. Sometimes it hides, and then there's the fire that dazzles, the kind used in stage effects and magic tricks. Alcohol flames burn so cleanly they can be nearly invisible, especially in bright daylight. That's why laboratory fires are so dangerous without careful observation. They vanish until they touch something that reveals their shape. In the right conditions, even invisible flames can cast shadows, their heat distorting the air and bending light like a lens. The edge of perception is where fire becomes art. Chemical fire demonstrations often involve adding salts to change the flame's color. Lithium makes a soft pink. Barium burns apple green. Potassium gives off a faint violet that's hard to see unless the background is completely dark. Each of these metals, when burned, throws off a different pattern of light, one that can be measured, mapped, and remembered. There's a kind of poetry in how fire expresses itself this way, not in shape or form, but in radiance. It is the language of transformation, each hue marking a different path of decay or birth. Even the blue core of a butane flame, often thought of as normal, is not a baseline, but a carefully balanced display. It's what happens when air mixes evenly with fuel. When the reaction becomes efficient enough to vanish soot and leave only the energy behind, it's not just temperature that determines fire's appearance, it's structure. In a candle flame, the outer region glows brightly because particles are still combusting. The dark center is a mix of vaporized wax and air that hasn't yet reacted. Between them is the luminous region, where the combustion is most active and visible. What looks like a simple flicker is a layered gradient of chemical stages, each color born from a different balance of fuel, oxygen, and heat. And in all these layers, in all these colors, is a truth we rarely think about. Fire isn't trying to glow. It glows because energy has nowhere else to go. It glows because electrons must fall. The light is incidental, a byproduct of transition, but we've learned to read it like a message, to interpret it as signal, meaning, danger, beauty. We watch a flame and see emotion, but the flame sees none of us. It simply burns, and in burning, it speaks red, orange, yellow, blue, white, violet, invisible, a silent spectrum, rising through temperature, shaped by chemistry, fading into wavelengths beyond the reach of sight. And somewhere inside all of that, we find warmth, we find light, we find something ancient, something familiar, and something still waiting to be fully understood. In space, fire forgets how to stand. It loses its teardrop shape, its pointed flicker, its dance with air and gravity. Without an up or down, there's no rising heat to stretch the flame into a tongue. Instead, It curls into a perfect, quiet sphere, hovering like a ghost, as if someone whispered a light into a drop of fog. The first time astronauts saw it, they didn't quite know what to call it. It didn't move. It didn't flicker. It simply glowed soft, blue, and still. On Earth, fire rises. That's the first thing we're taught. Hot air expands, becomes lighter, and rushes upward, pulling new oxygen in from below. This is convection, and it gives fire its familiar lean and sway. It's why flames always point toward the sky, even when they're burning sideways in the wind. The heat creates a current, a rhythm, a breath that feeds the flame and shapes it. But take away gravity, and the breath stops. In the microgravity of orbit, flames become slower, smaller, and eerily calm. There's no buoyant lift to stir them, so they smolder at their center, drawing oxygen only through the slow, lazy diffusion of molecules bumping and wandering in random directions. The result is a flame that burns cooler, rounder, and with a kind of patience. It doesn't flick. It doesn't roar. It just exists. These are called flame balls. Not a poetic term, but a scientific one. Delicate, spherical fires that form when combustion balances itself perfectly in all directions. They are only a few centimeters across and difficult to sustain, but they burn cleanly, efficiently, and with a quiet that seems unnatural. On the International Space Station, these tiny globes of fire have been studied carefully, suspended in midair, glowing softly inside sealed chambers. No sparks, no smoke, just a warm, steady shimmer of fuel and air learning to mix without help. In one experiment, researchers introduced droplets of heptane and methane into microgravity and ignited them. The resulting flame hovered like a bubble, feeding off the vapor that slowly drifted outward. As the fuel burned, the sphere shrank, drawing in on itself, still alight. Then, something stranger happened. Even after the visible flame disappeared, combustion continued dark, invisible but measurable. The fire was still burning, but it no longer glowed. This discovery unsettled expectations. On Earth, when a flame goes out, it's out. But in space, the absence of glow doesn't mean the absence of fire. This hidden phase of combustion, quiet oxidation without visible flame, suggests that fire is more persistent than we thought. It can adapt, it can vanish from sight and continue its work in silence. And what's even more intriguing is what this teaches us about fire down here, in the world of gravity and wind. The way fire moves on Earth isn't just a property of fire itself, it's a consequence of its environment. Gravity makes fire dance. It makes it rise, flicker, roar. Without gravity, those behaviors disappear, and what's left is the core reaction. Fuel meeting oxygen, releasing heat, rearranging molecules. The flame ball is fire at its essence, stripped of showmanship, stripped of noise, just chemistry suspended in time. In zero gravity, the soot doesn't rise either. There is no draft to carry particles upward, so they gather near the flame, dimming it, choking it. On Earth, soot is swept away, blackening the air above, but giving the flame space to keep breathing. In space, fire must reckon with its own residue. It becomes more sensitive, more fragile. A tiny imbalance in oxygen or fuel can starve it, or smother it. And yet, it endures. Watching these flames move or not move is hypnotic. They drift gently across the chamber, not because the fire is propelling them, but because any motion, however small, continues unchecked. There's no friction, no ground, no weight. A flick of the wrist sends the entire apparatus floating, and the fire follows. Not pulled upward, not flattened by turbulence, but suspended in stillness. There's something almost alive in it, not because fire breathes, but because it responds. It shapes itself to its world. In microgravity, it contracts into the smallest stable shape possible. On Earth, it reaches, stretches, grows legs and arms of heat. We think we know what fire looks like, but what we recognize is just one version, shaped by the pull of the planet beneath our feet. The flames aboard the ISS aren't just scientific curiosities. They're puzzles with consequences. Understanding how fire behaves in microgravity is critical for safety in orbit. A fire in space doesn't just rise and trigger a smoke detector. It hangs in place. It spreads differently, more slowly, but more unpredictably. And the smoke, instead of rising to the ceiling, pools around the flame or clings to surfaces. It moves only when something pushes it. That changes how we fight fires up there, how we design life support systems, how we build future habitats for the moon or Mars. And beyond safety, there's insight. The flame balls, the slow-burning orbs of methane and oxygen, show combustion we can't observe on Earth. They let scientists isolate variables, test new models, refine our understanding of chemical kinetics and heat transfer. These tiny, quiet fires, flickering in the silence of orbit, may help design more efficient engines, cleaner fuels, better ways to burn here at home. Back on Earth, we watch fires twist and climb, casting shadows on walls, warming our hands, lighting our streets. But we rarely think of how much of that motion is not fire itself, but gravity's influence. When fire escapes gravity, it reveals itself as something else, something slower, purer, and oddly elegant. A small flame on Earth burns fiercely, dancing with every breath of air, every subtle shift in the room. In space, it holds perfectly still. No wind to disturb it, no ground to anchor it. Just a soft, glowing bubble in the air, untouched by direction, held in suspension by nothing but its own will to continue. It burns differently, but it still burns. Water is supposed to kill fire. That's what we're taught. Water cools, smothers, drowns. It's the enemy of flame, the end of heat, the breath that fire cannot take. But in the deep corners of nature and industry, that rule begins to bend. And in some places, it breaks entirely. There are fires that live beneath the waves, that burn where no air should reach, where the pressure is crushing and the cold is constant. These aren't accidents. They're phenomena, flickers of combustion in realms that were never meant to ignite. Start with magnesium, a dull, silvery metal, deceptively light in the hand, used in flares, fireworks, and once, airplane parts. When it burns, it doesn't just glow, it erupts. The flame is white and blinding, hot enough to cut through steel, to burn your eyes, even when turned away. But its most remarkable property is this: water can't stop it. In fact, water makes it worse. When magnesium burns, it reaches temperatures above 3,000 degrees Fahrenheit. At that point, water doesn't act like water anymore. It doesn't cool, it splits. The heat tears H2O into its elements, hydrogen and oxygen, and those, as it happens, are both flammable. The result is a reaction that feeds on the very thing we meant to fight it with. Instead of smothering the flame, the water joins the combustion, a reluctant accomplice. Underwater, magnesium keeps burning, spitting bubbles of flame through, liquid, untouched by drowning. This kind of fire doesn't rage, it insists. It crackles with a slow defiance, immune to the surrounding cold. You could toss it into a lake, and it would vanish for a moment, then reappear, glowing from beneath, a hidden eye of light blinking back at the surface. And then there are the oil fires. We often think of oil and water as opposites, but in truth, oil just floats. It spreads across the top, a slick, shimmering skin that hides more than it reveals. When oil catches fire on water, it seems like a paradox. The surface ablaze, the depths untouched. But these are real, and they are dangerous. In ocean disasters, like the burning oil wells of the Gulf or the towering flames of offshore rigs, water becomes a stage for fire instead of a shield against it. These fires spread like liquid heat. The oil rolls and laps, and the flames follow, licking the surface, skating across waves with a grace that borders on unnatural. You can't douse them with seawater. The fuel is already on top, and every attempt to stop the spread risks making it worse, splattering oil, breaking it into new currents, feeding the fire instead of ending it. Sometimes, the only option is to burn it off deliberately, to sacrifice the fuel to the flame so it doesn't poison the sea any further. Controlled burns, they call them. Fire as containment. But even deeper, beyond the reach of sunlight or industry, fire finds another home. Along the ocean floor, where tectonic plates crack and the earth opens its slow wounds, underwater volcanoes erupt with a fury that belies their silence. Here, magma spills into the ocean, not just warming the water, but boiling it, forcing it back into vapor, lifting plumes of steam into dark currents. It's not combustion in the traditional sense. There's no oxygen, no flickering flame, but it is heat, and it is transformation. And in many ways, it is fire by another name. The lava that erupts underwater is different, too. It cools faster, yes, but it doesn't freeze instantly. As it touches seawater, the outer layer solidifies into glass, trapping the molten core within. Sometimes, it explodes from the sudden pressure. Other times, it stretches, bends, and rolls forward like thick taffy, glowing faintly beneath the crust, a slow river of heat at the bottom of the world. And around these hydrothermal vents, life gathers, not despite the fire, but because of it. Here, in the darkness, microbes feast on the minerals that pour from the Earth's deep wounds. Tube worms and ghostly fish flourish where the temperature swings from freezing to scalding in moments. They survive without sunlight, drawing energy not from the sky, but from chemical reactions sparked by heat. In this realm, fire doesn't destroy, it creates. This kind of fire doesn't light the dark, it warms it from within. In some places, deep beneath ice-covered lakes or sealed within machinery, fire breaks the rules again. In chemical reactors, under immense pressure, substances combust in supercritical water, water heated and compressed until it behaves like a gas and a liquid at once. In that state, it becomes a solvent for organic material, breaking it down with brutal efficiency. It burns without flames, digesting instead of incinerating. It's used to destroy waste, to clean toxins. Fire as purification, not spectacle. Even lightning has been known to start fires underwater, though only in shallow conditions. A strike can superheat a pocket of water, flash boiling it, sending shock waves through mud and sediment. If the conditions are right, the disturbance can release trapped gases, and a spark, however brief, can ignite a flame that dances, briefly and brightly, beneath the surface before vanishing again into the cold. It all points to one truth. Fire is not confined to the dry and the open. It is not afraid of water. It can burn beneath it, within it, alongside it. It only needs the right mix heat, fuel, and the chance to act. What we think of as fire is only one expression, the one we know best. But beyond the fireplace and the forest, beyond the match and the stove, fire hides in strange places. It bubbles beneath oceans. It glows inside steel. It whispers through reactions we can't see. And when it does burn underwater, it doesn't rage or roar. It persists, quietly, impossibly, defiantly, just as it always has. Cold fire is not something you see. It's something you realize too late, too quietly. It doesn't roar, doesn't flicker, doesn't warm your skin or light the dark. It drifts in silence, unfolds without warning, and disappears just as softly. We've built our understanding of fire around heat and light, around motion and destruction. But there are stranger versions hiding beneath that definition, lurking at the edge of what we think fire is supposed to be. Some of them glow dimly, some not at all. Some burn below the boiling point of water. They are real, they are rare, and they defy almost everything we assume. Cold flames were first noticed in the 1800s, in the cramped rooms of early chemists who were searching for answers without realizing they were stumbling into mystery. They'd mix air and ether in sealed chambers and return hours later to find it had ignited, not in a flash or bang, but in a soft shimmer, a faint blue haze hanging just above the surface of the liquid. No heat, no smoke, no obvious cause. And yet the reaction had happened. Material had been consumed. Fuel had vanished. But where was the fire? We call them cold, but they're not freezing. The term only means colder than what we expect from a flame typically hovering around 150 to 300 degrees Celsius, far below the thousands of degrees a normal fire produces. Still hot enough to burn your skin, to boil water slowly, to cause harm if left unchecked. But they don't spread like wildfire. They don't glow like candles. They creep, they linger, and they consume with unnerving patience. In a cold flame, the chemical reaction is incomplete, and deliberately so. The fuel oxidizes, but without reaching the ignition temperature that triggers bright, visible combustion. That means no orange flare, no yellow leap, no heat roaring upward, just a whisper of conversion, a rearrangement of molecules behind the curtain, and the flame itself often hides in plain sight. In low-light conditions, it might show up as a faint blue aura, delicate and flickering, like a breath caught in glass. But under daylight, it vanishes. You could walk past it, wave your hand through it, never knowing you were interrupting a burn in progress. This makes cold flames dangerous in ways that feel almost poetic. Fire that denies its own nature. Fire that doesn't warn you it's alive. They are incredibly difficult to reproduce. Too much heat, and the flame becomes hot, ordinary, bright, familiar. Too little oxygen, and the reaction dies out. The balance is razor thin, requiring exact conditions of pressure, concentration, and fuel type. Jet fuel is a favorite medium, JP10, a dense, high-energy hydrocarbon used in missile engines. When vaporized and exposed to just the right conditions, it can enter a cold flame state, oxidizing slowly and steadily without ever catching light. In this mode, the reaction is almost surgical. Bonds break and reform with precision, stripping energy from the fuel without the spectacle. If a normal fire is a storm, a cold flame is a clock. Clean, meticulous, efficient. It doesn't scorch or char. It doesn't leap from surface to surface. It eats only what it's given and asks for nothing more. But the strange thing is how stubborn it is. Once started, a cold flame can persist. In microgravity environments, where convection doesn't disturb the balance, it can linger for hours, slowly digesting its fuel in a chemical trance. On the International Space Station, scientists have studied cold flames with a mix of awe and unease. In one experiment, a droplet of fuel was ignited in microgravity. The visible flame burned out quickly, as expected, but the sensors kept detecting combustion long after the glow had faded. It wasn't an error. The fire was still there, just invisible. A ghost consuming the droplet from the inside out, perfectly stable, perfectly silent. It wasn't until years later that the implications began to settle in. Cold flames might offer new paths for combustion engines, ways to burn fuel more cleanly, more slowly, with less pollution and more control. They might also help us understand unexplained engine failures, spontaneous ignitions in places we thought were safe. Because cold flames don't behave like regular fire. They ignore alarms and escape detection. In the wrong setting, they can start without warning, and once they do, they don't cry out. Dark fire is another term for it. Not black flames in the way fantasy imagines. This isn't supernatural, but the darkness is real. A fire that burns without light, without smoke, without shape. In the laboratory, it's almost impossible to track without specialized sensors. And in the real world, it may be responsible for more than we realize. Equipment that degrades mysteriously, fuels that vanish without a spark, rooms that smell of combustion without a single mark on the walls. It's tempting to think of cold flames as weaker versions of fire, as something less. But they're not. They're just different. And in many ways, they're more precise. A traditional flame wastes energy and heat, in light, in the chaotic leap of molecules reacting all at once. Cold flames take their time. They extract only what they need. They burn like thought instead of action. And perhaps the most unsettling part is this. They exist on the boundary between ignition and inertia, between energy and stillness, that thin margin where fire begins but refuses to bloom. They remind us that combustion isn't an on-off switch. It's a spectrum, a slope, a quiet unfolding that can shimmer or roar or whisper or sometimes say nothing at all. In a world that teaches us fire is red and yellow, hot and wild, loud and consuming, cold flames rewrite the rules. They show us a version of fire that doesn't want to be seen, a version that waits in silence, a version that burns without light. Inside you, something is always burning, not with flame, not with light, not with smoke curling through your chest, but with quiet, constant fire. Every heartbeat is a kind of ignition, every breath fuel drawn in, and every step you take is powered by combustion not of wood or gas, but of sugar and oxygen, mingling in your cells in a slow, invisible blaze. You are not simply alive, you are a flame, always, from the inside out. This fire is not born in the lungs or the heart, but in the mitochondria, the tiny powerhouses curled deep inside nearly every cell in your body. They are ancient descendants of once free-living organisms that were swallowed by other cells over 1 billion years ago and never left. They kept their own DNA, their own systems, and they brought something essential, the gift of controlled fire. They are where oxygen meets carbon, where energy is unwrapped from its chemical chains, and where the body becomes something more than structure, where it becomes motion, thought, heat. We call the process cellular respiration, but it's closer in spirit to the engine of a slow-burning candle. Glucose, the sugar pulled from your food, is broken down into smaller molecules, carried into the mitochondria, and offered up to oxygen. When they meet, electrons leap from one molecule to the next, cascading through delicate membranes, releasing energy in careful steps. Not all at once, there's no explosion, but in a measured cascade, like coals smoldering just hot enough to heat a kettle without ever boiling over. And just like combustion, this process releases carbon dioxide and water. Every exhale carries the ghost of that reaction. When you breathe out, You're not just pushing air, you're releasing the ash of your internal fire, the spent breath of the sugar you used to move, to think, to be. The heat you radiate on a cold day, the way your skin glows slightly warmer than the air around you, that is the warmth of your metabolism at work. That is fire-wearing skin. Calories, in this context, are not just units of food, they're measurements of potential flame. 1 calorie is the amount of energy it takes to raise the temperature of a single gram of water by 1 degree Celsius. When you eat, you're not just nourishing tissue. You are fueling a reaction, feeding the inner furnace that never goes out. Even at rest, even asleep, your body is consuming oxygen, breaking molecules apart, keeping the embers alive. You are never truly still. Your fire is always hungry. This is why you generate heat when you exercise. Why your heart races. Why you pant. Your body is stoking the fire. Muscles demand more oxygen, more sugar. The mitochondria go into overdrive. The combustion rate rises, and with it, your internal temperature. If it weren't for sweat and circulation, you'd overheat, just like a machine left running too hard for too long. We are self-cooling engines, regulating our own burn. Yet it's not only heat that this internal fire gives, it's everything. Your thoughts ride on the electrons set free during respiration. The signals leaping through your brain are powered by tiny gradients built by that same quiet reaction. The movements of your fingers, your eyes, your breath, all fueled by the same steady spark. If that fire were to stop, everything would unravel. Death is not the absence of thought or motion. It is the end of combustion, the extinguishing of the body's last flame. Some creatures burn slower than us. The sloth, whose heart beats less than half as fast as ours, has a lower metabolic flame, a quieter fire. Others burn faster. Hummingbirds consume half their body weight in sugar every day just to keep up the furious pace of their wings, their hearts pounding over 1,000 times per minute. They are flickering flames, alive on the edge of burnout. And deep beneath the ocean, in the icy dark, there are life forms that burn so slowly their metabolisms stretch across centuries. Their fire is barely there, like a coal buried in ash. Even in the stillness, we are thermodynamic creatures. We are governed by the flow of energy, the balance of inputs and outputs. Too much fuel, and we store it, bank it in fat. Too little, and the body slows the fire, conserving energy, redirecting it to vital systems. Fever is a stoking of the flame, the body turning up the heat to fight infection. Shivering is a sudden burst of fire in the muscles, trying to warm the blood. Every reaction, every defense, traces back to this elemental equation. How to keep the fire going just long enough. We don't often think of ourselves as combustible. We associate fire with destruction, with danger. But the truth is, fire is how we live. In fact, we're surprisingly flammable. Fat and protein and carbohydrates are all energy-rich. Our bodies are packed with potential heat. It's only the precision of our internal chemistry, the containment, the control that keeps us from bursting into open flame. We are walking bonfires, neatly managed by millennia of evolution. In a sense, this is what makes life miraculous. Not that it burns, but that it burns so carefully, that it can sustain flame in every cell, every second, without destroying itself. Fire wants to spread, it wants to consume, but in our bodies, it's held back, directed, harnessed, not with walls or wires, but with enzymes, membranes, feedback loops, a biochemical choreography as elegant as any dance of flame. And yet, sometimes, that balance tips. In disease, cells may burn too fast or too slow. In cancer, the fire becomes unregulated, cells consuming and multiplying with reckless abandon. In hypothermia, the fire falters, the heat drains away, and the machinery begins to slow. Even in moments of extreme emotion, terror, rage, desire, the body flares up, heart pounding, pupils wide, blood rushing. These are flares in the mind's own engine, sparks leaping up from the steady burn beneath. You are not a machine, but you are powered like one. Every memory, every muscle, every dream, every laugh, all of it, drawn from the flame inside your cells. And long before we learned to make fire with stone or match, it was already within us, passed down from the earliest microbes that learned to breathe and burn in the same breath. That fire never went out. It burns in you still, quiet, hidden, essential, a steady blaze in the dark. The sky has burned before, not in the way we light matches or tend hearths, but but in moments so vast and violent that the atmosphere itself became part of the flame. These were not just fires, they were transformations, atmospheric upheavals so intense they lit the heavens, reshaped the land, and left scars in stone, ice, and wood. Most were not witnessed by human eyes, and yet the memory of them lingers in layers of ash, in tree rings, in the silicate glass fused into the earth. Evidence of fire too large for forests, too bright for the eye to look upon. One of the most astonishing of these moments happened in June of 1908 in a remote part of Siberia near the Tunguska River. Without warning, the morning sky cracked open with light. A fireball, brighter than the sun, streaked across the horizon. Then came the shockwave, an explosion that flattened over 800 square miles of forest, snapping trees like twigs, scorching bark, throwing people to the ground more than 40 miles away. There was no crater, no impact site, just silence and devastation. Trees laid down in radial patterns, all pointing away from the center, an invisible epicenter for a fire that fell from the sky. The best explanation we have is that a meteoroid, perhaps 50 meters across, entered the atmosphere at tremendous speed and exploded mid-air with the energy of 1,000 Hiroshima bombs. It never touched the ground. Instead, it disintegrated in the upper layers of the sky, releasing all its kinetic energy in a fireball hot enough to ignite the air itself. The light was seen across continents. For days afterward, skies across Europe glowed in eerie twilight, so bright that people could read newspapers at midnight. The air had burned, and yet, this was not the first time the Earth had seen fire from above. Throughout its history, the planet has been shaped by cataclysms, volcanic eruptions that turned day into night, nuclear detonations that mimicked the heat of stars, and wildfires so massive they etched their presence into the annual growth of trees. Mount Tambora, in 1815, erupted with such force that it ejected more material into the sky than any volcanic event in recorded history. The column of ash rose nearly 25 miles high, injecting sulfur and dust into the stratosphere. The explosion was heard thousands of miles away. Fire rained from the sky as incandescent pumice stones and ash buried entire villages. But the greater fire was in the atmosphere itself. The particles released reflected sunlight, disrupting global temperatures. The following year, 1816, became known as the year without a summer. Crops failed. Snow fell in June. The sky, once blue, turned a dull, smoky gray across much of the world. And then, there is the fire we made ourselves. In 1945, when the first nuclear test, codenamed Trinity, was conducted in the deserts of New Mexico, witnesses saw something they would never forget. A mushroom cloud climbed into the stratosphere, glowing orange and white, pulsing with heat that turned sand into glass. The fireball expanded in silence for the first few seconds faster than sound. Itself, then came the roar, a shock wave that knocked observers to the ground. The temperature at the center of the explosion briefly exceeded that of the sun's core. For the first time in human history, we had kindled a flame so hot it breached the boundary between physics and fear. These were not isolated events. They are echoes of a deeper truth. Earth has always burned, and sometimes it burns so fiercely that even the sky cannot look away. But not all these fires come with names or witnesses. Some are buried in time. Charcoal deposits in sediment layers tell of ancient wildfires that once scorched vast stretches of land. Some date back hundreds of millions of years, when oxygen levels were higher and vegetation thicker, creating the perfect fuel for continent-spanning blazes. Trees tell the story too. Within their rings, scientists can read the years of fire, the darkened bands that mark seasons of smoke and heat. Some trees, like the bristlecone pines, have survived multiple fire epochs, their rings holding a timeline of Earth's burn history stretching back millennia. There are even traces of wildfires in Antarctica, embedded in ice cores, revealing that even the coldest corners of the world are not immune to flame. Soot carried by wind, particles blackened by combustion, preserved in snow that fell centuries ago. Fire travels. It leaves its fingerprints far beyond its origin. Some researchers believe that massive ancient lightning storms sparked fires that reshaped entire ecosystems, forcing species to adapt or perish. In this way, fire acts not just as a destroyer, but as an agent of change. It clears the old. It births the new. It is part of Earth's metabolism, not just a symptom of disaster, but a mechanism of renewal. Even now, In the age of satellites and sensors, we struggle to grasp the full scale of these elemental events. When Australia burned in 2019 and 2020, the smoke rose into the upper atmosphere, circled the globe, and returned again. Instruments on the International Space Station watched it unfold. Day became night in the outback. Orange skies loomed over cities. The heat was so intense it generated pyrocumulonimbus clouds, firestorms that created their own weather systems, lightning and wind, and sometimes even spawned new fires. Flames feeding on flames, a loop of ignition that mirrored the forces once thought reserved for only the gods. In these moments, we glimpse the ancient face of the Earth, not the calm, green planet we see from space, but a restless world of energy and pressure, a world where, given the right moment, the sky itself will burn. Fire is not confined to hearths or torches. It exists at planetary scale, at atmospheric depth, in celestial collisions and human ambition. It is older than our species, and it will outlast us. And when it comes, when the sky catches fire, it does not ask permission. It does not wait to be seen. It arrives like memory from a time before memory, and it leaves behind only silence, smoke, and the lingering scent of something that should not have burned but did. Far above us, beyond air and cloud and the reach of flame as we know it, fire takes on another form, a form vast and ancient, unbound by gravity, untethered from wind or fuel or spark. The stars, scattered like lanterns across the fabric of space, are not just lights. They are fires, colossal, continuous, relentless. Every one of them is a furnace, burning not with wood or oil or oxygen, but with fusion, the binding of atoms, the smashing together of nuclei in a ceaseless war of pressure and heat. It starts with hydrogen, the most basic and abundant element in the universe. In the hearts of stars, gravity pulls hydrogen atoms into such close proximity that the forces keeping them apart begin to break down. Under the immense pressure, atoms fuse into helium, and in the process, a small fraction of their mass is released as pure energy, following Einstein's simple, merciless equation, E equals mc squared. It's a small amount of matter lost, but the energy it unleashes is immense. A single second of the sun's fusion reaction produces more energy than all of humanity has ever used, combined. Every flicker of starlight is a release of ancient energy, radiating across space at the speed of light. But this kind of fire doesn't dance or flicker. It roils, it churns. The surface of a star is in constant turmoil, riddled with convection currents that rise and fall like tides made of flame. Sunspots mark cooler regions. Solar flares erupt like angry exhalations, releasing radiation that can disrupt satellites and kiss our planet with auroras. The sun, to us, may seem steady, but it's seething, always, beneath its golden skin. Unlike earthly fires, stars don't need oxygen. They don't consume in the way logs do. Their fire is born from density, from time, from a battle between collapse and explosion. Gravity presses inward, trying to crush the star, under its own weight. Fusion pushes outward, fighting to expand. The star lives in the balance, teetering between implosion and detonation. As long as fusion continues, the star burns in equilibrium, bright, alive, stable. But this balance cannot last forever. When the hydrogen at a star's core is exhausted, the equilibrium begins to falter. The core contracts, and the outer layers expand, cooling as they stretch. The star becomes a red giant. In this bloated state, it begins to fuse heavier elements, helium into carbon, carbon into oxygen. Each step yields less energy, until eventually the process becomes unsustainable. For smaller stars, like our sun, this ending is gentle. The outer layers are cast off in glowing waves, forming delicate nebulae that drift through space like ink in water. The core remains behind, a white dwarf no longer burning, just cooling slowly, the ember of a once mighty flame. But for massive stars, the finale is far more violent. In the largest stars, fusion continues until iron is formed, and then it stops. Iron is the end of the road. Fusing it consumes energy instead of releasing it. Without the outward pressure of fusion, gravity wins. The star's core collapses in on itself in less than a second, and in that collapse, an unimaginable shockwave is born. The outer layers rebound and are blasted into space in a detonation so powerful it outshines entire galaxies. This is a supernova. For a brief moment, a single point in the sky becomes brighter than all the stars around it. Light from the explosion travels across time and distance, sometimes reaching us millions of years later, a sudden flare in our night sky from a death that happened long before we learned to look up. And in that moment of destruction, something extraordinary happens. Elements heavier than iron, gold, uranium, platinum are forged in the fury, scattered across the cosmos like seeds. Everything we are, everything we touch, that is, heavier than iron, was born in fire so great it tore itself apart to give us life. We are, quite literally, made of stardust. Supernovae don't just end stars, they also begin stories. The shockwaves can trigger the collapse of nearby gas clouds, birthing new stars. One fire ends, and another is lit. It is a cosmic cycle of ignition and ash, a relay race of fusion that stretches across billions of years. Some stars, instead of fading or exploding, go even further. If a star is massive enough, its collapse doesn't stop at a white dwarf or neutron star. It falls all the way in, past the point of light, past the rules of matter. It becomes a black hole, a place where gravity becomes so intense that not even fire can escape, not even light. The star's fire, so furious in life, vanishes into silence. And yet, the space around it glows as matter spirals in, heating to millions of degrees, screaming in X-rays before it disappears. The fire still lingers. At the edge of nothing, fire in the stars is not like fire on Earth. It is not wild, not chaotic, not hungry in the same way. It is disciplined, sustained. It lasts for billions of years, burning with such patience that it becomes easy to forget what it really is: a reaction, a fury, a war inside a sphere of gas. And when it ends with elegance or fury, with silence or violence. When you look at the stars, you are seeing the past light that left those fires before humans ever walked the earth. Some stars you see no longer exist. Their fire died long ago, but the light has only just arrived. We are always late to the story of the stars, always reading their final chapters before we even knew their names. And yet, their fire burns on in us, in the calcium of our bones, in the oxygen we breathe, in the gold we wear. Fire in the stars made fire in the earth possible. Without fusion, there would be no carbon, no water, no planets, no people, just hydrogen and silence. So when you gaze upward at night, understand this. You are not just looking at light, you are looking at fire. Ancient, disciplined, immortal fire. Fire that has seen the birth of galaxies. Fire that still echoes inside every living thing. Fire that waits, patiently, to be remembered. Lightning doesn't ask for permission. It arrives with no warning, a searing rift between earth and sky, cleaving the atmosphere with the sound of torn air and the smell of burning ozone. In that single instant, longer than a heartbeat and shorter than a thought, it turns night to day and silence to rupture. But beyond the spectacle, beyond the blinding flash and guttural crack, lightning is fire's swiftest messenger, a carrier of ancient energy, a spark that doesn't just strike, but ignites. At its heart, lightning is not made of light or flame, but of plasma, a state of matter so hot, so unstable, it tears electrons from atoms and leaves a trail of charged chaos in its wake. When lightning forms, it does so, invisibly at first. Deep within a thundercloud, turbulence stirs up ice crystals, hailstones, and water droplets, charging them like particles in a blender. Positive charges collect at the top, negatives settle at the bottom, and the earth below, sensing this electric imbalance, responds in kind. The tension builds, the air strains, and then, in a moment of surrender, a narrow finger of electrons lashes down from the cloud, seeking, searching. It never touches the ground on the first attempt. Instead, it steps downward in fits, jagged and unsure. And from the ground, unseen to the naked eye, tiny filaments of charge reach up to meet it. When they finally connect, the channel is complete, and energy rushes through at incredible speed, heating the air to over 30,000 degrees Celsius. That's 5 times hotter than the surface of the sun. The air expands explosively, creating the thunderclap that trails the flash. But the flash itself, that narrow line of plasma can reach, for miles. And in that brief corridor of fury, fire is born. Dry trees, brittle grass, desiccated soil, anything combustible within reach of the strike becomes a potential wick. Fires born of lightning can smolder for hours before flaring into visibility, hidden in the base of a tree or the roots of dry brush. This is how many wildfires begin. not with arson or accident, but with a single bolt falling from a storm no longer in sight. One flash, one ember, a forest changed forever. In deserts and beaches, lightning strikes sand and leaves behind something rare. Fulgurites. These are natural glass sculptures, thin and branching, formed when the strike melts silica in the sand and fuses it into solid structure. They are petrified lightning evidence of fire's arrival in a place that could not hold it. Sometimes they twist for meters below the surface, hollow and delicate like the roots of an invisible tree. They are reminders that even the earth itself can momentarily liquefy in the presence of enough energy. But lightning does not confine itself to fair skies and forests. Sometimes it finds its way into the mouths of volcanoes. Volcanic lightning is one of nature's most unsettling sights, a storm born not from cloud and rain, but from ash and lava. During a violent eruption, ash particles explode upward in a column miles high, colliding with such ferocity that they become electrically charged. The result is a furious storm cloud made of rock, hurling bolts of lightning from its edges like something out of myth. This lightning doesn't wait for a thunderstorm to roll in. The volcano creates its own weather, and in doing so, its own fire. Each bolt a signature of the earth's anger, inscribed on a sky thick with smoke. And then there is the strangest spark of all, a phenomenon that has eluded full explanation for centuries. Ball lightning. It appears as an orb glowing, drifting, often silent. Witnesses describe spheres the size of grapefruits or basketballs, hovering above the ground, rolling along fences, floating through open windows. Some last for only seconds. Others persist, pulsing, changing color, even making a faint hissing sound. There are accounts of ball lightning entering homes, sliding along ceilings, and vanishing without a trace. Others end with explosions, scorch marks, or the acrid smell of ozone. No one fully understands how it forms. Theories range from vaporized silicon compounds to microwave interference. But what's certain is this: it is lightning unbound, fire decoupled from strike, a spark given shape and autonomy, refusing to obey the rules. These are the fires born in an instant, not coaxed from flint and tinder, not kindled with care, but unleashed by nature's raw will. They don't always stay. Often, the flash is the whole story, a bright ribbon drawn across the sky and then gone. But sometimes, what's left behind is not silence, but smoke. The slow curl of fire awakened by speed. Even our ancestors feared and revered lightning. To some, it was divine punishment, the wrath of gods hurled from mountain thrones. To others, it was the gift of flame, like the myth of Prometheus, who stole fire from the heavens. In every corner of history, lightning has been both destroyer and benefactor. It can kill a tree in an instant, or grant the spark that leads to civilization. In our modern age, we've tamed many kinds of fire. We build it into engines, ovens, circuits, but lightning still escapes us. We can't predict where it will strike, nor capture it at scale. It belongs to the wild sky, to the clash of clouds in charge. And when it strikes, it does so with complete authority. No negotiation, no mercy, only transformation. Because sometimes, the world changes not slowly, but all at once, with a sound like the sky cracking in half, with a thread of light so fast the eye cannot follow, with a fire that begins in a fraction of a second and lingers long after the storm has passed. Before fire destroyed, it built. Before it raged through forests and danced atop candles, it crouched low in the center of a ring of stones, whispering heat into meat, drying damp hides, and casting flickering shadows onto the walls of caves. Long before cities rose, before writing, before the wheel, fire was there, crackling softly in the cold night, a silent witness to the first sparks of humanity. It was both tool and teacher, a glowing presence that turned the darkness into a place of gathering, where warmth replaced fear, and embers promised something more than just survival. We didn't invent fire, we discovered it. At first, perhaps, from the sky, a lightning strike igniting a dry field, a volcanic vent lighting the earth from below. But it didn't take long before we began to see what it could do. Not just cook, not just warm, but change things. Fire softened roots, too tough to chew, drove predators away, lit paths through the unknown, and over time, we stopped, fearing its hunger, and began to feed it ourselves. Bits of bark, twisted grass, the edge of a fallen log. In learning to tend fire, we began to shape the world. Charcoal was among our first alchemies. By burning wood slowly in low-oxygen pits, early humans created something stronger, lighter, and more efficient than firewood. Charcoal burned hotter and longer, unlocking temperatures that simple flames couldn't reach. With it, fire crossed a threshold from something used to something that could transform. It was with charcoal that fire first began to act like a forge. Clay, hardened in the coals of open fires, was another quiet revolution. At first, it was a matter of utility, vessels to carry water, bowls to hold grain. But those pots told stories. They bore the fingerprints of their makers, the impressions of woven mats, the thumb-pressed patterns of people who shaped earth and trusted fire to make it last. Fired clay didn't just hold things it endured. It turned dust into memory. Even today, when all else has vanished, shards remain, sleeping in the soil, the fire that hardened them still locked in their structure. But it was metal that truly revealed fire's power to build. In the heat of a carefully stoked furnace, copper could be coaxed from green stone, not poured like in stories, but extracted slowly, painstakingly. Later came bronze, an alloy of copper and tin, stronger and sharper, and with bronze, we began to cut more deeply into the earth, to clear forests, to carve paths, to shape not just tools but societies. Smelting became a kind of ritual. Ore crushed into powder, mixed with charcoal, buried in clay crucibles and heated until the rock wept metal. This was more than just chemistry, it was vision. Seeing in fire not destruction, but transformation. The forge became sacred. Blacksmiths, keepers of heat and hammer, were both craftsmen and conjurers. They made plowshares that could break soil, swords that could defend borders, nails that could build homes and temples. Every civilization that rose did so with fire at its core. Fire in the hearth, fire in the kiln, fire in the forge. Glass came later, a strange child of sand and flame. When desert lightning struck silica-rich beaches, it sometimes left behind glassy, twisted forms, nature's fulgurites. But humans learned to control this magic. By heating sand, soda, ash, and lime to extraordinary temperatures, they pulled from fire a material that could be both fragile and eternal, transparent and strong. With glass, they shaped beads, vessels, lenses, windows, ways to see, to contain, to reflect. Each of these inventions, charcoal, pottery, metal, glass, was a step toward civilization, but they were also expressions of something deeper, a relationship. We didn't just use fire, we collaborated with it. We gave it fuel, air, shape. In return, it gave us tools, protection, permanence. It let us rise beyond the limitations of bone and sinew, of claw and tooth. Fire gave us an edge that wasn't sharp, but subtle. It let us manipulate the materials of the earth. It let us imagine something, then make it real. Even cities owe their existence to fire. Bricks hardened in kilns stacked into walls, lime burned into mortar, metal girders, glass facades, concrete poured in steel molds, none of it possible without flame. Fire was there in the first spark of a flint on dry moss, and it's still there in the glowing filaments of our furnaces and factories. We don't sit around campfires as often now, but the fire is still with us, hidden in wires, stored in batteries, roaring in engines, coursing through turbines and igniting in the bellies of rockets. And through it all, fire has remained both familiar and strange. We shape it, and it shapes us. It's easy to think of fire as something that only destroys, but from the beginning, it's been our silent partner in building. Brick by brick, tool by tool, light by light, fire does not hate what it burns. It doesn't seek revenge or express anger, it simply consumes. In its most unbound form, fire is not a weapon or a punishment, it is a process. Indifferent, immediate, absolute. And yet, to the human eye and heart, it can feel like fury incarnate, a wildfire racing down a hillside, a home turned to embers, a factory ripped apart by an explosion that echoes for miles. When fire leaves its rings of stone and steel and spirals out of control, it becomes something else entirely. It becomes destruction. But destruction is not always a matter of malice. Fire destroys with the same mechanism it builds, with oxidation, with heat, with hunger for fuel. It is only our perspective that changes the meaning of the flame. A controlled fire inside a kiln becomes a sculpture. The same fire, untethered, becomes loss. Wildfires often begin unnoticed. A careless ember, a cigarette flicked from a window, a lightning strike hours away from sight. At first, the smoke may seem gentle, a drifting column over distant trees. But wind can coax fire into motion. It feeds on pine needles, dead leaves, dry bark. It climbs branches like ladders, and once it gains speed, fire becomes a living thing. It leaps gaps, it creates its own wind, drawing in oxygen with a low roar like an animal breathing. Temperatures rise, flames stretch, trees burst. What once smoldered now gallops across terrain, reshaping entire ecosystems in a matter of hours. From above, it looks like a moving wound, bright edges against blackened earth. From within, it is chaos. Ash and sparks caught in cyclones. The air itself glows. And yet, fire doesn't distinguish between the tree and the house, the fence and the forest. It consumes what burns. That's all. The line between natural fire and disaster is thin. Some wildfires are necessary. Entire ecosystems depend on them. Certain seeds only open in flame. Forests clear themselves through burn cycles, allowing new growth to thrive. But the fires we fear most are not these natural pulses. They are the ones that creep into neighborhoods, that cross roads, that climb walls. A house fire begins as quietly as a breath, a candle tipped over, an overloaded socket, a forgotten pan. At first, it's a flicker, a whisper of smoke curling toward the ceiling. But materials inside homes, synthetics, foams, plastics burn hotter and faster than wood. Rooms can become unsurvivable in minutes. Smoke blinds, heat radiates. And suddenly, the place that once held your memories becomes a box of fuel. It isn't the flame that kills most often. It's the smoke, thick with carbon monoxide and toxic gases. It fills lungs before fire even touches skin. Flashover, the moment when everything in a room ignites at once, can happen in less than 5 minutes. Windows explode. Beams fall. Sirens scream in the distance. But by then, the structure may already be lost. And then there are explosions. Not slow burns, but sudden violence. Combustion condensed into a heartbeat. When fuel and oxygen mix in just the wrong ratio, when a spark finds them at the perfect moment, the result is instant release. A fireball, a shockwave, glass turned to sand, metal folded like paper. Explosions have no center. They radiate in all directions, flattening everything with the blunt force of temperature and pressure unleashed all at once. Factories, oil rigs, grain silos, yes, even flour can explode under the right conditions. It's not the material itself, but its form and suspension in air. Fine dust becomes a cloud becomes a bomb. And in those moments, fire is not just destructive, it is mythic, the kind of event spoken of in hushed tones, described in words that never quite capture the sound, the heat, the finality. But fire is not evil. That's the hardest thing to hold on to when watching it take a home, a forest, a life. There is no malice behind the flame, no will to punish. It simply follows the laws of nature. It moves where there is fuel and heat and air. It is chemistry and physics, not punishment. We fear fire because it cannot be reasoned with, because it does not stop when we plead, because it turns the familiar into smoke. And yet, fire is not always the end. In some forests, the burn is followed by bloom. In cities, homes are rebuilt with fire codes tighter, exits clearer, walls stronger. In grief, there is remembrance, and in remembrance, there is a kind of rebuilding. Fire clears, but it also reveals. It forces the eye to see what mattered, what was irreplaceable, what we took for granted. To destroy is part of fire's nature, but so is transformation. The same heat that shatters can also purify. The same flame that consumes can illuminate. In this, fire mirrors us more than we care to admit. Capable of devastation, yes, but also of beauty, change, and, sometimes, renewal. We can never make fire safe, only safer. We can never make it tame, only tamed for now. But we can. Remember that even in its most terrifying form, it is not a villain. It is a force. It is up to us how we live alongside it. Air, as we know it, doesn't burn. You can wave a torch through it, throw sparks into it, fan it with bellows or the wind of your breath, and it will never catch. Yet without air, without the invisible mixture swirling around us, there would be no fire at all. The paradox lies in the details. Oxygen, the quiet accomplice to every blaze, isn't flammable on its own. It doesn't ignite. It doesn't spark. but it is the key that turns the lock of combustion. It's not the flame, it's the reason the flame exists. On Earth, roughly 21% of the atmosphere is oxygen. That number seems small, but it's perfect, an exquisite balance struck between breath and burn. Any less, and fire would struggle to hold. Kindling would hiss but fail to ignite. Flames would die in their infancy, and even the most careful campfire would gutter out without warmth or smoke. But any more, and the world would become a tinderbox. A lightning strike could ignite forests with unnatural ease. A dropped match could set entire towns ablaze. Fires would rage faster, hotter, harder to contain. It would be like living in the exhale of a forge. The Earth has not always had this balance. In the early days, long before lungs and leaves and bones, there was barely any oxygen at all. The planet's first fires were volcanic, chemical, explosive, not reliant on the kind of combustion we know today. It took the rise of photosynthetic life, tiny cyanobacteria drifting in ancient seas, to begin filling the air with oxygen, and when that process took hold, it changed everything. The Great Oxygenation Event flooded the atmosphere with a gas that allowed for a new kind of fire, one that could live in the open air, one that could start with a spark and end with transformation. Once plants had reshaped the sky, fire became a permanent part of the landscape. For millions of years, atmospheric oxygen has hovered near the same range, not by chance, but by feedback. Too much fire, and plant life suffers. Less plant life, less oxygen. The system checks itself, keeping combustion possible, but not inevitable. Still, there have been times when that balance shifted, subtle changes, invisible to the eye, that made a world more flammable. In the Carboniferous period, around 300 million years ago, oxygen levels soared above 30%. Insects grew to monstrous sizes, dragonflies as wide as eagles, millipedes longer than your leg. And fires? Fires were different too. With such oxygen-rich air, even damp vegetation could burn. Lightning could set entire swamps alight. Charcoal deposits from that era show wildfires were not just common, they were colossal. It was a world where the very air encouraged flame, a planet inhaling and exhaling with fire at its edges. If Earth had just a few percentage points more oxygen today, the consequences would be profound. A spark could become an inferno in seconds. Firefighters would face blazes more resistant to control. Houses would burn not in hours, but in minutes. And our own breath, so dependent on oxygen, might begin to betray us. The risk wouldn't be in breathing too much, but in living too close to the edge of ignition. Every flick of a switch, every cigarette, every friction-made spark would carry more danger. On the other hand, if oxygen dipped too low, the opposite would occur. Fires would suffocate, engines would stall, even candles would struggle to hold their glow. We'd breathe harder, run slower, tire more easily. Our atmosphere is a tightrope act, walked with each inhale, but oxygen isn't the only player in the story. The rest of the air, the nitrogen, argon, carbon dioxide, acts as ballast, diluting the volatility. It spaces the oxygen out, keeps the flames in check. In pure oxygen, materials combust explosively. A wire, in normal air, glows gently in a light bulb. Place it in pure oxygen, and it erupts with blinding brightness. Fabrics that would never catch can suddenly vanish in a flash of light and heat. Even steel can burn in the right conditions. Astronauts are intimately familiar with this danger. Inside spacecraft, oxygen levels are carefully controlled, often lower than atmospheric, to prevent fire from finding a foothold. The tragic Apollo 1 accident in 1967 was a stark reminder of oxygen's dual nature necessary for life, but merciless when conditions tilt. A test in a pure oxygen environment led to a fire that consumed the capsule in seconds, killing all 3 crew members before they could escape. It was a silent lesson written in flame. Oxygen may not burn, but it can make everything else burn faster, harder, without warning. The truth is, we live in a planet-wide compromise. We breathe the same air that fuels every wildfire. We inhale the same substance that lets a single match bloom into warmth. The atmosphere doesn't just carry clouds and weather. It holds the invisible boundary between combustion and calm. Fire, for all its noise and motion, is patient. It waits in the ratios, in the percentages of gases that float unnoticed around our heads. It doesn't ask for much, just the right mixture. A little dry kindling, a spark, and suddenly, something quiet becomes something irreversible. The air we live in, the one we so casually ignore, is flammable enough to burn entire continents, but only when the balance tips. And that balance is fragile, kept by forests and oceans, by ice and carbon, by the slow churn of life itself. A planet that burns, but doesn't blaze. A sky that breathes, but doesn't ignite. We are surrounded by the ingredients of fire every moment of our lives, yet we rarely see them for what they are. The invisible tension that makes fire possible and civilization manageable. So we walk, unknowingly, through flammable air, and we trust that the world will keep breathing just right. Some fires do not crackle. They do not cast shadows on cave walls, nor paint the air with ribbons of orange. These fires don't light the night, and they can't be seen with the naked eye, but they burn all the same quietly, invisibly, relentlessly. Their presence isn't marked by flame, but by heat, by radiation, by the subtle hum of energy moving where vision fails. These are the fires you can't see. We think of fire as a spectacle, something we watch, dance, and flicker. But that dance is only one narrow slice of the story. The visible flame is just a sliver of a broader phenomenon, confined to the narrow band of electromagnetic radiation our eyes are built to detect. Beyond the reds and oranges, past the yellows and whites, fire keeps going, spilling into the realm of the invisible, into the deep glow of infrared. Infrared is heat made visible if only you had the right eyes. To snakes, that heat is as clear as movement. Pit vipers can detect the body heat of a mouse in total darkness, navigating not with sight, but with thermal impressions. Fire, to them, is not light but shape, not flicker but contour. And through the lens of a thermal camera, you too can see fire's afterlife, the ghost of heat it leaves behind. A log, blackened and still, may seem cold to you, but in infrared, it pulses softly. A stove turned off hours ago still radiates warmth. A car engine whispers in colors your eyes were never taught to read. Even the sun, the source of nearly all warmth on Earth, burns across the spectrum. Only a fraction of its radiation is visible to us. The rest spills into ultraviolet, into X-rays, into long waves of infrared. On cool nights, you can feel that radiation linger, not the flame itself, but its residue, its echo. Heat is the signature fire leaves behind, and it can travel far, skipping across vacuum, untouched by wind or air. Radiant energy, moving not through matter, but through space itself. In some parts of the world, the air seems still, the sky quiet. But satellite eyes tell another story. Forests burn in silence beneath heavy canopies. Peat bogs smolder underground for weeks, unnoticed by anyone walking above. Only thermal imaging reveals the slow creep of these subterranean fires. They can tunnel through the earth for miles, hidden from sight, immune to rain, resistant to time. The earth's skin glows with invisible flame, and we only see it when we borrow the senses of machines. In war zones, infrared tells its own version of history. The wreckage of tanks still warm to the touch, shells that glow white in thermal view as they cut through the night. Even breath becomes visible, a fog that blooms and vanishes. Fire is there too, in the form of explosions, in the fever of machinery, in the slow burn of fuel. But to the human eye, these fires often go unnoticed. It's only when you look in infrared that the full tapestry reveals itself, an unseen world stitched together by heat. And there are other fires, stranger still, that don't burn in any traditional sense. Fires that exist as radiation, not flame. Consider the surface of a neutron star so hot it radiates in X-rays, or a quasar whose light has traveled for billions of years, still flickering with the energy of ancient combustion on a galactic scale. These are not fires you could stand beside. They would erase you before your nerves could register pain. Yet they radiate with the same fundamental principle: the release of energy, the transfer of heat, the persistence of light beyond sight. Closer to home, combustion can be tuned to wavelengths we cannot detect. Certain chemicals, when burned, emit in the ultraviolet. The flame is there, but you will never see it unless you use a special lens. Other flames are so low in energy they barely glow, existing in a kind of twilight between visibility and darkness. They're called cold flames, but their mystery lies in their lightlessness. You can feel their heat, you can measure their chemistry, but you won't find their glow flickering on the wall. Sometimes, even humans emit a kind of invisible fire, not in myth, but in biology. The warmth of your skin is a slow, steady burn. Stand in front of a thermal sensor, and your outline glows in oranges and purples, brighter at the forehead, the hands, the heart. You are not ablaze, not in the usual way. But inside every cell, mitochondria crackle with molecular combustion, breaking sugars, releasing energy, powering your every breath and blink. This is what fire becomes when it sheds its visible cloak. Not a spectacle, but a process. Not a flame, but a field of energy. It becomes something that must be felt, or translated, or trusted. Something that leaves traces we can only interpret through tools and inference. The fires you can't see are no less real than the ones that dazzle. In some ways, they are more honest. They don't show off. They don't dance. They simply continue, smoldering in roots, echoing through space, riding on infrared waves through the dark. And if you tune your perception just slightly beyond the ordinary, you'll find that fire is all around, hidden not by absence, but by spectrum, waiting, not to be lit, but to be noticed. Every fire, no matter how grand or fleeting, begins in the quiet space between molecules. It isn't born with a roar. It doesn't demand attention at first. It starts instead as a whisper in the language of chemistry, a chain of decisions at the atomic level, a vote cast by carbon and hydrogen in favor of release, reaction, and release again. Combustion is not magic, but it feels like it. At the heart of every flame is a process both violent and elegant. Oxidation. It's a reaction between a fuel and an oxidizer most often, something rich in carbon meeting the oxygen in our atmosphere. But that encounter isn't instant. Before anything can burn, the molecules must be coaxed. They need a push. This is where heat enters the story not as fire, but as ignition. Enough energy must be applied to break molecular bonds. You can't rearrange a sentence without first undoing a few letters, and the same is true in chemistry. Bonds must break before new ones can form. This initial energy input is called the activation energy. It's what a match provides to a candle wick, what friction provides when striking flint. It's not the fire itself, but the permission slip. Once the bonds break, new ones form in rapid succession, and energy is released. That energy takes the form of light, of heat, of expansion. This is the fire we see. The glow, the warmth, the flicker, all byproducts of a deeper molecular transformation, fuels vary wildly. Wood, gasoline, ethanol, natural gas, even sugar. All of them are made mostly of carbon and hydrogen atoms, arranged in different chains and rings. These atoms are like tightly packed springs, storing chemical energy until something invites them to let go. When fire consumes a log, it doesn't destroy matter. It reorganizes it. Carbon bonds break, and new bonds form with oxygen. The carbon becomes carbon dioxide, the hydrogen becomes water vapor, and the heat spreads outward in all directions, carrying the memory of those vanished molecules. The flame itself is a structured thing. Though it may look like a chaotic dance, it's an orderly zone of reactions. Closest to the fuel is the inner core, where vaporized gases rise but have yet to burn. This region is often blue, starved of oxygen, rich in fuel, and hot. Just above this lies the luminous region, the part of the flame that glows orange and yellow. Here, combustion is complete or nearly so, and particles of soot are heated to incandescence, giving the flame its color. Above that is the outer plume, where the last of the unburnt gases meet the surrounding air. In this halo, the fire cools, the reactions slow, and heat dissipates into the environment. The shape of the flame, the way it points upward, flutters in breezes, leans with breath, is not a mystery of spirit, but of fluid dynamics. Heated air is less dense and rises. Cooler air rushes in below to take its place, feeding the reaction and shaping the fire's motion. It's a loop, a breath, a rhythm. Some flames are fast and hungry. Gasoline ignites quickly, releasing energy in an almost explosive rush. Others are slower, more contemplative. A hardwood log can smolder for hours, releasing its energy in long, soft waves. But the chemistry beneath is largely the same. The equation remains. Fuel plus oxygen plus heat yields combustion. Endothermic reactions, those that absorb heat, sometimes precede this. The vaporization of fuel, for instance, steals heat from the surroundings, which is why fire often dies in wind or rain. Enough energy must stay in the system to keep the chain reaction alive. If too much is lost, the fire collapses inward and extinguishes itself, like a thought interrupted mid-sentence. Combustion is deceptively simple in its ingredients and endlessly complex in its execution. The smallest variables, moisture content, air pressure, fuel arrangement can tip the scales. A fire might leap or stall, roar or retreat, all depending on the delicate balance of conditions. And it is delicate. That's part of the wonder. Fire doesn't happen by default. It isn't the natural state of matter. It requires a very specific agreement between elements. Carbon must agree to let go, oxygen must agree to bind, and heat must show up just long enough to get things started. After that, the process becomes self-sustaining until the fuel is gone or the conditions change. It's worth remembering that even though fire feels wild, it is bounded by these rules. You can start a fire with flint or with lightning or with a lens and sunlight, but never without permission from the molecules. That's what makes it beautiful. Not its chaos, but its constraint. In a way, flame is a translator. It takes chemistry and renders it visible. Every flicker is a sentence written in atoms. Every crackle is a paragraph of stored energy made audible. When we stare into a fire, we're watching the rewriting of matter itself, the rearrangement of molecules into simpler forms. We are watching the universe solve a puzzle of entropy, one bond at a time. And though it may appear primal and ancient, the chemistry of flame is a window into some of the most fundamental truths of reality. That energy can be stored, that bonds can be broken and remade. That light is a byproduct of change. In the language of fire, everything burns in sentences of carbon and oxygen, and we, standing nearby, warm our hands by the glow of molecular poetry. Fire has always been more than heat and light. Long before it was a tool, it was a mystery, a flickering presence that seemed to breathe and dance, to consume without touching, to appear from nothing and vanish into smoke. It was alive, without being living. Wild, yet strangely obedient. Fire didn't just change food or forge tools, it changed the imagination. It demanded to be seen not just as physical force, but as symbol, spirit, and story. And so, nearly every culture, every faith, every myth spun its own meaning around the flame. To the ancient Greeks, fire was divine theft. Prometheus, Titan, and trickster scaled the heavens to steal fire from the gods and bring it down to humankind. It wasn't just a gift of warmth or cooking. It was power, knowledge, civilization itself. For this, he was chained to a rock, punished eternally by an eagle devouring his regenerating liver, a visceral image for the price of progress. In fire, the Greeks saw rebellion and consequence, creation and punishment bound together in flame. In Zoroastrianism, fire is not metaphor, it is sacred in its very reality. Temples are built around flames that are never allowed to die. These fires are tended constantly, kept clean, fed, only. Pure wood. They're not prayed to, but prayed near. They serve as the presence of Asha truth, order, and the divine spark in all living things. In a world where chaos is always near, the fire is a reminder that clarity and balance can be maintained if carefully nurtured. Hinduism too reveres fire as more than element. The god Agni is the messenger between worlds, carrying offerings from earth to the heavens. In rituals, flames consume clarified butter and rice, transforming them into invisible essence and delivering them skyward. To sit before a sacred fire in India is to sit at the edge of two realms. It's why marriages are sealed by circling the fire, why births and deaths are marked by it. Fire is the witness, the purifier, the bridge. The eternal flame appears again and again in the story of human meaning-making. The Vestal virgins of Rome tended a fire in the Temple of Vesta that was never to go out. It represented the heart of the empire, the continuity of state, the presence of divinity within civic life. Its extinguishing would be considered an omen of collapse. The idea of an unbroken flame became a symbol of unbroken promise, of watchfulness, memory, and sacred duty. Even in secular spaces, the eternal flame persists. In memorials to fallen soldiers, we light fires that never end. At the tomb of the unknown soldier, at memorials in Pearl Harbor or Hiroshima, the fire is not there to warm or cook. It burns as presence, as witness, as if flame itself could remember what words cannot say. Ceremonial fires are scattered across cultures like glowing threads on a shared tapestry. In Japan, the fire festival of Kurama sees flames carried through the streets to welcome spirits. In Bali, fire dances drive away demons. In Celtic traditions, the Beltane fires were kindled to protect livestock and call in the sun's strength for the growing season. Fire has been used to ward, to summon, to to mark beginnings and endings. It's in the center of funeral pyres and in the candles of birthday cakes. It's in the incense of churches, the lanterns of Diwali, the Hanukkah menorah. The same force that can raise a city is also what we place on top of a birthday cake to celebrate another year of life. And perhaps that's what makes fire such a potent symbol. It holds opposites at once. It is destruction and rebirth, in danger and safety. It clears forests and fertilizes them. It consumes, but also transforms. In myth, fire often signifies the soul or spirit because it cannot be held, yet it is felt. It flickers, it ascends, it disappears, leaving only warmth and ash. Like us, in Christianity, fire becomes both judgment and comfort. The Holy Spirit appears as tongues of flame at Pentecost, alighting on the apostles as a symbol of inspiration, courage, and speech. Yet in other passages, fire is a place of trial, of refinement, of purgation. Gold is purified by flame, so are intentions. Fire, in this light, is the ultimate test what remains, after everything untrue is burned away. Native American traditions hold fire as a teacher. In many tribes, the central fire in a circle is not just for heat or light, but for communication with ancestors, with spirits, with the land. The crackle and hiss are part of the conversation. Fire does not speak in words, but it listens, and it gives back through warmth, vision, and presence. Even the modern world, wrapped in wires and screens, returns to fire in moments of ritual. We light candles for the dead. We strike matches on holidays. We gather around campfires, not because we need to, but because it feels ancestral. The flicker of a flame in a dark room quiets the mind in a way no artificial light can. It taps into something older than language, the memory of safety, the awareness of danger, the awe of transformation. For all our science, we have never outgrown the mystery of fire. We understand the combustion reactions, the temperature gradients, the plasma states. And still, we write poems, we light votives, we stare, entranced. Because fire is more than physics. It is presence. It is passage. It is the breath of myth, still flickering at the edge of our vision. There is a kind of magic in seeing fire consume the unexpected. Not the usual wood or oil, but something strange, something ordinary turned volatile. It reminds us that combustion isn't loyal to appearances. It isn't only born from the traditional hearth or gasoline flame. It can leap from the unlikeliest materials, erupting in silence or thunder, hiding within the everyday, waiting for the perfect conditions. Fire doesn't care if something looks innocent. It only asks if the fuel is willing and if the energy is ready to be released. Sugar, for example, seems harmless. Sweet, crystalline, familiar. But under the right conditions, sugar becomes explosive. When dispersed into fine particles and mixed with air, it becomes a cloud of fuel, sensitive, eager, and waiting for a spark. It's not the sugar in your coffee that's dangerous, but the dust floating unseen in a grain silo or candy factory. A single ember, a static discharge, even the friction of a moving part can ignite it. What follows is sudden and devastating. An eruption of heat and light as billions of tiny molecules break apart and reform in an instant. Entire buildings have vanished in this way, devoured by the sweetness they once produced. Peanut dust behaves the same way. So does flour. So do many organic powders when suspended in air. What seems benign becomes combustible art, a fire hidden in dust, needing only to be disturbed and awakened. In these cases, the strangeness isn't in the fuel itself, but in the form it takes tiny particles with vast surface area, giving oxygen more room to rush in and set everything ablaze. These are fires born not of logs and kindling, but of clouds and chaos. Some fuels are stranger still. Thermite is a mixture of powdered aluminum and iron oxide rust. When ignited, it creates a reaction so hot, it doesn't just burn through metal, it melts it. The reaction doesn't rely on oxygen from the air, so it can burn underwater or in the vacuum of space. Thermite is used to weld train tracks together, to disable equipment in emergencies, to produce light and heat beyond the reach of most flames. Once it begins, it cannot be stopped. No water can quench it. It glows white hot, like the heart of a star, consuming its ingredients with ruthless efficiency. And when it's gone, it leaves behind slag and steam, and a silence that feels scorched. Magnesium is another metal that burns with a kind of purity. When lit, it produces a brilliant white flame, nearly blinding in its intensity. It can burn even in carbon dioxide, even in nitrogen atmospheres, even in the presence of water. Water, in fact, only feeds it splitting into hydrogen and oxygen and adding fuel to the fire. This is not a gentle flame. It is sharp, electric, unyielding. It feels like something that shouldn't exist outside a laboratory or a forge. Yet it can be found in fireworks, flares, and even old camera flashbulbs. It's light that sears, both in temperature and in memory. Then there is burning ice. It sounds like contradiction, but it is real. Clathrate hydrates structures of water molecules that trap natural gas inside can be lit even as they appear frozen. On the ocean floor, in cold, high-pressure environments, these icy cages form and store methane. When brought to the surface, and if conditions align, they can be ignited. The ice begins to melt, but the gas it releases catches fire, producing a ghostly scene. Flames dancing atop a melting block of ice. It is fire fed by freezing, a contradiction only on the surface, like so much of the natural world. Even something as odd as banana peels can burn, though not in the way most might imagine. Dried and pulverized, the fibrous content of banana skins rich in carbon and volatile. Compounds becomes flammable. It can smolder like wood shavings or burst like dry leaves. The same goes for coffee grounds, orange peels, and coconut husks. Waste, in one form, becomes energy in another. The line between trash and fuel is thinner than it seems. And then there are metals. Titanium, zinc, sodium, potassium, elements that, when shaved or powdered, ignite with eerie beauty and alarming ferocity. Potassium reacts with water so violently that it explodes into lilac-colored flame. Sodium sizzles with a yellow gleam. These are the fires that remind us how the periodic table isn't just theory, it's potential energy waiting to be unleashed. Strange fuels often hide in plain sight. The party trick of lighting a gummy bear in molten potassium chlorate isn't just spectacle, it's a microcosm of chemistry. The sugar in the candy reacts violently with the oxidizer, producing a screaming burst of flame and color. It's science dressed as chaos. It's fire-making, itself known in a place where delight and danger briefly overlap. Even hand sanitizer, clear, cool, and wet to the touch, can burn if the alcohol content is high enough. It's a flame that's nearly invisible in daylight, a pale blue flicker that doesn't announce itself but still consumes. Many have lit it without realizing how hot it is, how real, and yet, when it burns, it leaves nothing behind but vapor and surprise. The universe is built on transformation, and fire is one of its purest instruments. Whether from banana skins or rust powder, from frozen gas or metal shavings, combustion follows the same rules. A release of energy, a rearrangement of matter, a moment of irreversible change. These strange fuels only deepen the wonder, because they remind us that fire doesn't care about what we expect. It only cares about the chemistry. What burns is not always what you think will burn, and what looks harmless might already be waiting, quietly, to catch. There are moments when fire stops behaving like a thing and begins to behave like a creature. It gathers itself, lifts from the ground, and moves with purpose. The wind ceases to simply feed it. It becomes part of it, twisted into the body of the blaze, a spine of air wrapped in heat and hunger. These are the moments when fire walks, when it takes form, when the line between atmosphere and inferno blurs and the sky begins to burn. A fire whirl begins almost by accident. In a large wildfire, as the air above the flames grows hotter, it rises fast, pulling cooler air inward from all sides. If the terrain or wind direction tilts that inflow just right, the rising column begins to spin. A vortex forms air wrapping around air, pulling flame and ash and smoke into rotation. It's the same physics that gives birth to tornadoes, but instead of water vapor and dust, it's made of fire. Within seconds, what was a wall of flame can twist upward into a spiraling inferno hundreds of feet tall. A living column of heat that moves like a mindless predator across the landscape. From a distance, a fire whirl looks impossible, like a flame that has decided to stand upright. It sways and twists, its core white-hot and its edges shredding into sparks. The noise is unsettling, a deep, roaring hum, as if the air itself were screaming. These vortexes can travel faster than a person can run, hopping ridges, leaping roads, spawning embers miles ahead of themselves. The larger ones can uproot trees, lift cars, tear roofs from buildings, and hurl burning debris into the air like artillery. When the 1,000, 923 Great Kanto earthquake struck Japan. Fires broke out across Tokyo, and a massive fire whirl more than 300 feet across formed in the city's Hifukusho district. It devoured thousands in seconds, leaving only ash and silence. It was as if the atmosphere itself had turned on the people below. Fire whirls are the smaller cousins of something even more terrifying, the firestorm. Firestorm doesn't just burn within the weather, it creates its own. When enough heat is released in a concentrated area, the rising column of hot air grows so vast and violent that it generates its own wind system. Air rushes inward at the surface, feeding the inferno with oxygen. The updrafts become so powerful they can tear branches from trees and throw them skyward, where they ignite and fall back as flaming projectiles. The fire begins to move against the prevailing wind, defying meteorology. It doesn't just react to the weather anymore, it is the weather. During World War II, the bombing of Dresden and Hamburg produced such storms. Entire neighborhoods were set ablaze, and as the fires spread, the heat reached a tipping point. Winds of hurricane strength were pulled toward the center, feeding the flames faster than any human could comprehend. Oxygen was stripped from the air. Streets glowed as if the stones themselves were burning. People were lifted off the ground, drawn toward the heart of the storm. In those moments, cities became furnaces, and fire behaved as something beyond control, beyond even the imagination of those who unleashed it. In wildfires, the same forces can emerge naturally. The Black Saturday fires in Australia, the Car Fire in California. These events gave birth to firestorms that generated lightning and thunder of their own. At the Car Fire, a vortex of flame nearly 1,000 feet wide touched down with the power of an EF3 tornado, tearing apart steel transmission towers and melting them like wax. Firefighters called it the Dragon, a name earned not for poetry but for precision. It was fire that moved with its own will, bending metal, twisting wind, creating a roar that could be heard for miles. There was no line to hold, no water that could touch it, only retreat and waiting for the beast to burn itself out. Above the largest fires, the heat rises high enough to pierce the atmosphere's upper layers, forming pyrocumulonimbus clouds, thunderheads born of flame. These towering columns of smoke and ash climb 10 miles or more into the sky, billowing like volcanic eruptions. Inside them, particles collide and electrify, creating their own lightning. This lightning strikes back down, sometimes starting new fires miles from the original source. The fire feeds the cloud, and the cloud feeds the fire. It's a cycle of creation and destruction, a storm seeded by heat instead of water. Satellites have captured these clouds from orbit, vast plumes crowned with lightning, drifting like volcanic monsters across the continents. To watch one rise is to see the Earth rewrite its own atmosphere. You can feel the shift in the air even miles away, the sudden gusts, the strange pressure, the way the sunlight changes color. It's no longer simply smoke blotting out the sky. It's something bigger, something structural. The sky reshaped by heat, a column connecting the ground to the heavens, a flame so large it has grown its own weather system, its own ecology, its own presence. And at the heart of it all, the same principle as every campfire and candle: heat, fuel, and oxygen. The same chemistry, scaled up until it becomes a kind of planetary phenomenon. Fire walking across landscapes, climbing into clouds, pulling wind and water into its dance. It's humbling to remember that this, too, is physics. That the firestorms howl, the tornadoes spiral, the lightnings return, all of it is natural. Terrible, yes, but not malicious. Fire doesn't intend to destroy any more than gravity intends to pull. It simply fulfills its conditions. We tend to think of fire as grounded, something that belongs to the earth, to wood and leaves and soil. But when it grows large enough, fire ceases to belong anywhere. It invades the air. It takes the sky. It becomes movement itself. In the end, the phrase "fire that walks" isn't metaphor, it's truth. Because sometimes, when the world gets hot enough, the line between what burns and what breathes disappears, and the fire, no longer bound to the ground, rises. It strides forward through the wind. It learns, for a while, to walk. Fire has always been more than a force. In the right hands, under the right conditions, it becomes something else entirely. A dancer, a trickster, a performer. It sways to rhythms. It spins in place. It splits itself in two, or turns invisible, hiding in plain sight. And long before we understood combustion or chemistry, we knew one thing intuitively: fire could be beautiful. Not just beautiful in the way a sunset is, or a candle flicker on a quiet table, but beautiful in a way that feels alive, playful, like it's watching you back. In controlled settings, far from the chaos of wildfires or the power of furnaces, flame becomes pliable. In sound experiments, scientists create flames that dance not to the randomness of the wind, but to music, a Rubens tube. Essentially, a metal pipe filled with flammable gas and drilled with small holes lets us see the invisible. When sound is pumped through the tube, the gas vibrates in sync with the waves, ignite it, and the flames rise in perfect, rippling patterns higher at the peaks of sound, lower in the valleys. It's a concert for the eyes, a physics lesson rendered in heat and motion. Fire made to waltz to Beethoven or pulse to bass-heavy electronica, turning the airwaves into choreography. Other setups create spinning vortexes of fire, miniature versions of fire whirls, but under glass domes or steel cages. With just a fan or two and a steady flame, you can coax fire to spiral into a perfect, narrow tornado, controlled, predictable, hauntingly symmetrical. These lab-born firestorms don't destroy, they mesmerize. They show us how easily fire responds to shape, to airflow, to unseen patterns in the air, that it can be bent without being broken. In the world of performance, fire takes on a different mask. Fire breathers lace their mouths with alcohol and exhale plumes of flame into the night sky. The fire seems to bloom from their lips, trailing smoke and sparks. Fire dancers spin flaming poi balls of burning fabric attached to chains into hypnotic loops. When moved just right, these flames leave glowing trails in the dark, forming circles, spirals, figure eights. It's not the fire that's creating the illusion, but the limits of the human eye. Persistence of vision turns momentary motion into continuous light. In that space between real and imagined, fire becomes a paintbrush. Magicians and illusionists have long used fire as both spectacle and sleight of hand. Flames that appear from empty palms, papers that vanish into flashes of light, potions that burst into color on cue. Much of it is chemistry, precise blends of alcohols, salts, and powders that ignite at low temperatures and burn in vivid hues. Strontium for red, copper for blue, barium for blue, green. Some tricks use flash paper, made from nitrocellulose so light it feels like silk, but so reactive it burns away in an instant without smoke or ash. Fire appears, then disappears, like a whispered lie. There are illusions even in nature that feel like tricks. Willow, the wisps, those ghostly lights seen over swamps and marshes, were once thought to be spirits or lost souls. In truth, they may be caused by the spontaneous ignition of gases like methane and phosphine released from decaying organic matter. But knowing the chemistry doesn't diminish the eeriness. Imagine walking through a bog at twilight and seeing a pale flame hovering just above the water, drifting silently through the mist. That's not just combustion, that's folklore being born. Artists, too, have claimed fire as medium. Pyrography, writing or drawing with flame, burns designs into wood, leather, even paper. The heat darkens the surface, leaving behind lines like ink, but with a subtle depth and texture. Some artists use torches, others fine-tipped heating tools, building shadow and light, not with pigment, but with carbon. Each line is final. Each stroke smells faintly of smoke. It's art made permanent by risk. In some installations, flame itself becomes the sculpture. Kinetic fire art uses propane, air, and precise nozzles to create moving walls of fire, pulsing towers, breathing domes. At festivals like Burning Man, entire mechanical sculptures are built to shoot fire into the sky, synced with music, rising and falling in time with the beat. It's fire as architecture, fire as rhythm, fire made not just to burn, but to perform. Even beyond spectacle, there's a strange intimacy in learning how fire moves. Fire eaters don't just swallow flames, they master the currents of air, the physics of heat transfer. They know how to close their mouths at just the right moment to extinguish the flame before it can scorch. Fire jugglers practice for years to toss and catch, burning clubs without fear. Not because fire stops being dangerous, but because the danger is understood, managed. It's not defiance, it's dialogue. And for every visible trick, there are invisible ones. Flames shaped by magnetic fields, gas mixtures tuned to ignite only under precise frequencies, plasma trails that trace invisible paths through the air, sparking only when touched by laser or spark. These are fires that seem impossible. Fire that doesn't act like fire. Fire that waits. Through all of this, one truth remains. Fire is not just energy, it is language. Whether spun by dancers, painted by artists, manipulated by engineers, or sung into shape by sound, fire communicates. It speaks in movement, in pattern, in timing, and we, for all our control, are still listening. Because even when we shape it, fire never truly belongs to us. It can be guided, coaxed, danced with, but it remains a presence all its own, a partner in illusion, always on the edge of wonder and danger. A performer that remembers, at any moment, how to bite. In the aftermath of fire, when the air is still thick with smoke and the ground blackened to ash, something strange begins to happen. What looks like devastation is not an end, but an invitation. Beneath the scorched bark, inside the charred earth, life is already moving. Seeds crack open, roots stir, creatures emerge from burrows, blinking into a world remade by heat. Fire, so often imagined as a destroyer, becomes here a midwife. It strips away the overgrowth, resets the stage, and whispers, "Begin again." Some landscapes are not only tolerant of fire, they're designed for it. The longleaf pine forests of the southeastern United States, the eucalyptus groves of Australia, the chaparral shrublands of California. These places are built on a rhythm of burning. Their trees wear thick, protective bark, like armor, shielding the vital inner layers. Some even drop flammable oils into the underbrush, almost inviting the flames. To us, it looks reckless, but to the ecosystem, it's renewal. In these fire-adapted biomes, flames are not intruders but visitors, expected guests in a cycle that goes back millions of years. Without fire, some of these trees cannot reproduce. The cones of jack pines, for example, are sealed with a resin that only melts in high heat. Inside, the seeds lie dormant, waiting for the kiss of flame. When the forest burns, the resin softens, the cone opens, and the seeds fall to the ground onto bare soil, cleared of competition, enriched by ash. It's a gamble timed to catastrophe, a strategy written in fire. Eucalyptus trees take it further. Their bark peels in long ribbons that hang dry and paper-thin, like kindling waiting for a spark. Their leaves contain oils that are not just flammable, but explosive. In a blaze, these trees don't just burn, they intensify the fire, spreading it quickly across the canopy. And yet, their roots dig deep. Their buds lie buried beneath. Thick bark, ready to sprout, new shoots almost immediately. Within days of a fire, green tendrils emerge from blackened trunks. It's as if the trees had only been sleeping, waiting for their moment to wake. Beneath the trees, fire-loving seeds lie in wait. These are serotinous plants, whose germination is not triggered by time or water, but by flame. Some have coatings that fire cracks open. Others respond to the heat by releasing smoke-sensitive hormones, tiny chemical switches that say, now is the time to grow. Some seeds respond not even to fire itself, but to the compounds in smoke. In South Africa's fynbos and California's chaparral, entire plant communities bloom in the months after wildfire. A sudden, explosive response to the chemical language left behind by burning. Animals, too, have learned to live in these fire-born worlds. Some even thrive because of fire. The black fire beetle, Melanophila, can detect infrared radiation from fires more than 60 kilometers away. It doesn't flee from the heat, it flies toward it. The beetle lays its eggs in freshly burned trees, where the bark has been softened by fire and predators are few. Its larvae tunnel through the wood, safe in a habitat made possible only by flame. Other creatures are not so dramatic, but no less adapted. Burrowing animals like gophers, tortoises, and insects survive fires by going underground, waiting in cool tunnels while the inferno passes above. Some birds have even learned to hunt the fires themselves. In Australia, certain species of raptors known locally as firehawks have been observed picking up burning sticks and dropping them into unburned areas. This behavior spreads the fire, flushing prey into the open. It's not myth, it's observed strategy. Fire as a hunting tool, passed down through generations of beaks and talons. There are frogs that breed in the temporary pools left behind by firefighting efforts. There are fungi that only fruit after a fire, whose spores germinate in ash-rich soils. There are ecosystems that reach their peak richness not in long, undisturbed stretches of peace, but in the messy, chaotic aftermath of destruction. These places do not resist fire, they embrace it. And in doing so, they remind us that fire is not simply something to be survived. Sometimes, it's something to be depended on. The idea of fireproof and fireborne blurs in these places. To be fireproof is not to be untouched by flame, it is to be prepared. To be fireborne is not just to arise after fire, but to require it. These ecosystems evolved not in spite of fire, but because of it. Their rhythms match the flicker of flame, their strategies shaped by heat and renewal. In the absence of fire, they do not flourish. They stagnate. They overgrow. They forget how to begin again. For humans, this is a difficult lesson. We tend to view fire as something to eliminate, to control, but in fire-prone landscapes, suppression only delays the inevitable. The underbrush thickens, deadwood piles up, and when fire finally does return, it comes not as a cleansing wave, but as a catastrophe. We call it disaster, but often it is simply the land remembering what we tried to make it forget. To walk through a burned forest in its first spring is to witness something quiet and astonishing. Blackened trunks rise like sentinels, but between them, shoots of green poke through the ash. Flowers bloom where there was only smoke. Animals return in cautious steps, and the air, once sharp with soot, begins to carry the sweetness of new growth. It's not a return to what was, but a movement forward, a rebirth, not in spite of fire, but because of it. Fireproof and fireborne, words that sound like opposites but are, in many ways, the same. Resilient, adapted, time to flame. These are not just survivors, they are collaborators, partners in a cycle that began before we arrived and will continue long after we're gone. Not all life fears the fire. Some life waits for it. Fire has always looked backward and forward at once. It burns in the ancient rituals of our past, and yet glows in the heart of machines meant to carry us beyond Earth. It cooked our first meals, and will likely fuel our first steps on alien soil. The oldest tool we ever tamed is quietly shaping our wildest dreams. Not just a flame in the hearth, but a plasma jet in the vacuum of space, a thermonuclear pulse guiding us toward distant stars. Fire is both memory and prophecy. In the sterile belly of space labs and the humming cores of experimental reactors, the fire of the future isn't orange and crackling. It doesn't lick at logs or flicker in the wind. Instead, it pulses as plasma-ionized gas hotter than the surface of the sun, confined by magnetic fields into swirling loops of light. These are fires that require no oxygen, that don't even need air. They are born from the collision of particles and confined by physics most people never see. But at their core is the same hunger, transformation, energy drawn from potential, heat as a byproduct of becoming, controlled fusion. The dream of harnessing the same process that powers stars has become one of humanity's great quests. The promise is near mythic: clean energy with no carbon emissions, no long-lived waste. Just a few grams of hydrogen transformed into immense power, replicating what suns do naturally. In reactors like tokamaks and stellarators, scientists use superconducting magnets to shape and squeeze plasma into rings and spheres. The temperatures reach hundreds of millions of degrees. It is not fire in any traditional sense, but it is fire in spirit, raw, glowing transformation, held together by human ambition and the thinnest of margins. And then there are plasma engines, thrusters that use electric fields to accelerate charged particles and generate thrust. They don't roar like rockets. They whisper, silent, continuous, precise. Their flames are ghostly and pale, nearly invisible in the blackness of space. But they are efficient, capable of pushing spacecraft farther than chemical fuel ever could. Where traditional engines burn violently and briefly, plasma propulsion offers a patient kind of fire, one that doesn't explode, but endures. It is the difference between a sprint and a pilgrimage. As we imagine a future among the stars, fire must come with us. Mars, dry and barren, offers little in the way of natural combustion. Its atmosphere is too thin, mostly carbon dioxide, and what little oxygen exists wouldn't support an ordinary flame. But fire is not just something we use, it's something we need. To melt ice, to cook, to shape metals and build shelters. And so we will bring it with us, not as a flickering match, but as controlled arcs of electricity, solar concentrators, microwave heaters, machines that mimic fire's function, even when flame itself is impossible. terraforming, reshaping an entire planet to resemble Earth is an idea still firmly in the realm of speculation. But even here, fire plays a role. Theories suggest using orbital mirrors or greenhouse gases to slowly warm Mars, releasing trapped carbon dioxide and thickening the atmosphere. Controlled detonations or underground nuclear heat sources might trigger geological activity, coaxing life from frozen ground. These are not fires we'd recognize from a campfire or a forge. They are planetary-scale ignition points, designed not for destruction but for awakening. Fire as a sculptor of worlds. Even closer to home, the future of fire intersects with climate. As wildfires grow more intense, we study fire not just as a threat, but as a system. Fire ecology, prescribed burns, controlled ignition as a means of prevention. In the future, fire management may rely more on AI-guided burns, satellite monitoring, and drone-deployed ignition capsules. Technology will not replace fire, it will learn to speak its language better. 2. Guide it, not just fight it. To understand when to step aside and when to intervene. And yet, through all of this, through the plasma drives and fusion reactors, the Martian heaters and terraforming detonations, one thing remains the same. Fire is change. Whether it's a forest being cleared by flame to make way for new growth, or a spacecraft propelled by the exhaust of accelerated ions, the essence is unchanged. Energy, motion, evolution. Every fire, ancient or futuristic, begins with something that was stable and ends with something that is not. We often speak of fire as primitive, as though it belongs only to the past, but it might be the most forward-facing thing we've ever known. It carried our ancestors across ice and savanna, and it may carry our descendants across interstellar gulfs. It taught us to shape tools, to cook food, to create art, and it may yet teach us how to power entire civilizations without polluting them. What's remarkable is that the fire we light with a match and the fire we build in a fusion reactor are governed by the same rules. Thermodynamics, entropy, the transformation of one kind of energy into another. The fire in your fireplace obeys the same physical laws as the core of a star. The same truths that warmed ancient hands under the stars are now guiding our hands as we reach toward them. So when we imagine the future not just of fire, but of humanity, we are imagining a continuity. The torch isn't just being passed forward, it's being carried, carefully, relentlessly, across centuries and out into the void. Not as a symbol, but as a tool, a companion. The future is not cold, it burns. In a darkened room, a single candle flickers. Its flame is small, but it fills the space with a quiet, golden presence. We stare at it without realizing, lulled by the slow, rhythmic motion of light and shadow. No danger, no heat worth noting, just the gentle dance of combustion repeating the oldest show in human history. And yet we watch, transfixed, as if seeing something sacred, as if something inside us recognizes something outside us. The mind meeting the fire and remembering, long before we had books or clocks or walls, we had fire. In the vastness of prehistoric night, it offered the first border between safety and chaos. It cooked our food, kept predators away, and gathered us close in circles where stories were told. It wasn't just warmth, it was orientation. The flame gave shape to the dark and a center to the world. Our ancestors huddled near it not just for survival, but for connection, to each other, to themselves, to something deeper they couldn't name. That feeling has never left us. We don't need open flame anymore. Not really. Electric heat keeps us alive in winter. LEDs shine brighter and safer than any torch. But still, we light candles for birthdays, for prayers, for love, for loss. We crowd around bonfires at beaches and watch fireplaces crackle behind glass. We gather at dayed campgrounds not because the flame is necessary, but because it is familiar. Something about fire draws the body and quiets the mind. It is, in many ways, a meditation with movement. There's a term for this, biophilic response. The idea that we are wired to feel calm and soothed by natural stimuli, flowing water, rustling leaves, open skies, flickering flame. But fire is different from the rest. It's not just something we observe, it's something we once shaped and carried. Our evolutionary history is threaded with sparks and smoke. Watching fire calms our heart rate, lowers blood pressure, even changes our brain waves. Something ancient shifts into alignment, a ritual encoded in muscle and marrow. And though the world has changed, the rituals have not entirely disappeared. The gas stove, clicking and hissing into blue bloom, echoes the fires of older kitchens. The soft, warm light of a candlelit room speaks the same language as a torchlit cave. Even our screens, pulsing with moving light, mimic the hypnotic flicker of flame. We stare at phones in the dark the way we once stared at fires, letting the glow draw our thoughts inward. It's no coincidence that we call it screen time. The light holds us. Fire, reimagined, is everywhere. In the engine that propels a jetliner through the sky, in the crematorium where we say our final goodbyes, in the slow-burning incense of a temple, in the birthday candle blown out over wishes we hope someone, somewhere, is listening to. It's in our metaphors, too. A fiery passion, a burning desire, a spark of genius, to rekindle love, to be consumed by grief. Fire speaks the language of our emotions because it has always mirrored them, flickering, growing, erupting, fading. We don't just use fire, we identify with it. In its most comforting form, fire gives us a sense of control. A campfire can be tended, a hearth can be stoked, the flame on a wick can be lit and extinguished with a breath. These acts become symbols of choice and care, of attention paid. Lighting a candle can mark a transition from busy to still, from day to night, from ordinary to sacred. It signals presence, and presence is rare, but in its untamed form, fire reminds us of all we cannot control. It leaps, consumes, transforms. It resists boundaries and obeys no master. A house can vanish in minutes. A forest can turn to ash in hours. We fear fire because we recognize its potential to remake the world without permission. Yet even in that fear, there is awe. The same awe that once made us tell stories of gods who gave us fire or punished us with it. The same awe that fills us when we watch a lightning bolt fracture the sky and know what could follow. In this way, fire lives in our minds as both comfort and warning. It is the warmth of the familiar and the edge of the unknown, the glow we follow home and the spark we dare not touch. And somewhere in between those extremes lies something deeper, a memory that belongs not just to the individual, but to the species. To sit near fire is to participate in a lineage longer than any dynasty, more enduring than any empire. We have passed down this knowledge not just through instruction, but through presence. Watch the child at the bonfire. No one teaches them to stare. They just do. No one explains the rhythm of flames. They just follow it. It's as if fire speaks in a language we've always understood. And maybe it does. Not in words, but in movement, in warmth, in the way it gathers us without command, in the way it asks nothing but still gives everything heat, light, transformation. We sit beside it, and the mind slows. The noise of the world softens. The edges blur. And what remains is something elemental and quiet and whole. In the future, perhaps we'll forget the smell of wood smoke. Perhaps we'll trade flames for screens entirely, or for plasma confined in invisible chambers. But even then, the idea of fire, its symbolism, its psychology, its pull will remain. Reimagined, yes, but not replaced. Because fire is more than energy. It is memory, it is ritual, it is mind. And in its glow, something in us still remembers the first time we sat in the dark, reached out our hands, and felt the warmth of the world made visible.